Hello, this is Tor Lacey with a discussion about how the landscape at Joshua Tree National Park came to be. My main objective is to help you better understand why the landscape of Joshua Tree National Park looks the way it does. Joshua Tree National Park is situated in the easternmost transverse mountain ranges and includes the Little San Bernardino, Pinto, Hexie, Cottonwood, Eagle, and Coxcomb Mountains. The Transverse Ranges get its name from the fact that it trends transversely to the other mountain ranges in the western U.S. Joshua Tree contains parts of two of the four deserts of North America, the Mojave and the Colorado. These desert climates are geologically very young, having developed over the past several million years as the recently uplifted San Bernardino and San Jacinto Mountains have created a rain shadow for this region. Even more recently, in just the past 20,000 years or so, Earth has cycled out of a glacial period, warming and drying the climate. By the way, how do we know if we are in the Mojave or the Colorado Desert? Question: what principally controls the physical characteristics of any given landscape? The rock, of course. As you probably already know, there are three groups of rocks. Igneous rocks are masses of interlocking crystals that form from the solidification of magma or lava. Sedimentary rocks are the product of the weathering and eroding of pre-existing rock, forming from the deposition of solid particles or the precipitation of minerals. Metamorphic rocks form when the mineralogy and texture of a rock is altered by intense heat and or pressure. Question: what type of rock is chiefly responsible for the Joshua Tree landscape? Both igneous and metamorphic, but it is igneous rocks that are responsible for the landscape that creates the setting for most of Joshua Tree's attractions. Granitics, or granite-like rocks, are intrusive igneous rocks with felsic composition, making them light-colored. They form from slow-cooling magma deep underground, giving them a coarse-grained texture, with mineral crystals visible to the naked eye. Granitic rocks are, for the most part, what visitors observe in their campgrounds, at the exhibits, and along the interpretive trails in the park. Another common igneous rock is basalt. Basalt forms extrusively on Earth's surface and has a mafic composition, making it dark-colored. Malapai Hill, along Geology Tour Road, is made of basalt. How is granite made? Because granite is most important in terms of the landscape that draws people to Joshua Tree National Park, I'll discuss this rock in more detail. In order to talk about how granite is made, we also need to talk about plate tectonics. Let's start with Pangea, the name given to the supercontinent that existed from 280 to 200 million years ago. Starting around 200 million years ago, Pangea began to split apart as the continents started to move away from one another. So why would this happen? Let's consider that Earth has a layered structure, with the outermost layer being rigid. Think of a hard-boiled egg, with Earth's outermost layer being the shell. This outer shell of Earth is cracked into about a dozen large pieces, which we call plates. The movement and interaction of the plates is plate tectonics. Heat rises from the core as convection currents, pushing these plates apart in some areas, creating new crust, while gravity pulls the plates into Earth's mantle in other places, destroying old crust. In the case of Pangea, the rising heat caused the supercontinent to rift and split apart, and the different pieces of continental crust were pulled and pushed away from one another. Plates meet and interact along plate boundaries. Divergent plate boundaries are where two plates are moving away from one another, and convergent plate boundaries are where two plates are moving towards each other. In terms of Joshua Tree and the making of granite, we want to focus on convergent boundaries. Where a plate of oceanic crust collides with a plate of continental crust, the process of subduction occurs. Subduction makes magma, which rises towards Earth's surface. From this magma, continental volcanic arcs are constructed, like today's Cascade Range, where the Juan de Fuca plate is subducting beneath North America. At depth, magma is solidifying to make intrusive igneous rocks like granite. Let's take a closer look at this process as it pertains to Joshua Tree's geology. From around 200 million years ago to about 25 million years ago, a convergent plate boundary existed all along the entire length of the western margin of the North American continent, just like the Cascadian subduction zone discussed in the previous slide. During this time, the subducting plate was called the Farallon plate. The Juan de Fuca plate is the last remnants of this plate. This cross-section view shows the oceanic Farallon plate subducting beneath the North American plate. Let's go through the steps needed to form granite. 1. Heating causes water trapped in the subducted seafloor to escape. 2. This rising water is so hot that it partially melts the rock of the upper mantle, forming mafic magma, which, 3, rises and pools up beneath the continental crust. 4. Heat from this magma partially melts the continental crust, forming felsic magmas. 5 and 6. The felsic magma rises along with mafic magma, possibly mixing. And 7. Some of this magma may reach the surface to erupt as a volcano. Granitic rocks of Joshua Tree. Granitic rocks are felsic in composition, meaning they contain abundant feldspars and silica in the form of the mineral quartz. They may also contain minor amounts of the darker minerals biotite and hornblende. Several distinct granitic bodies make up the Joshua Tree landscape, spanning 3 geologic periods. Here's a summary of a few from oldest to youngest. From the Cretaceous period, we have the Palms granite, making up most of the rock outcrops west of Ryan Mountain. Squaw Tank granite appears to have solidified around the same time and can be observed along Geology Tour Road. The Jurassic Period White Tank Monzo granite, a granitic rock with more feldspar than quartz, is 150 million years old and makes up most of the granite east of Ryan Mountain. The oldest granitic bodies are from the Triassic period. The Queen Mountain Monzo granite is in the northern part of the park and the Desert Queen mine area, while the 29 Palms porphyritic quartz monzonite, also in the north, can be observed in the Indian Cove campground near Rattlesnake Canyon and is distinguishable because of its extra-large orthoclase phenocrysts. Intrusive igneous rocks can solidify into large, intrusive structures called batholiths. Along with the batholith, smaller tabular features called veins form as magma flows, then solidifies along cracks in rock. These features are exposed at Joshua Tree. Before going further, though, let's consider this question. How do granitic rocks that form 10 to 15 miles deep become exposed on Earth's surface? Let's summarize the steps needed to answer this question. Subduction makes magma. The magma rises as plutons, and as it does, cools, eventually crystallizing into a huge mass of intrusive igneous rock called a batholith. The pre-existing rock between the batholith and the surface is the country rock, original crustal rock, which at this stage forms a roof over the batholith called a roof pendant. Over the next tens of millions of years, erosion, isostatic uplift, and faulting all act to bring the batholith up to the Earth's surface. These batholiths make the core of the Sierra Nevada mountains and the Joshua Tree landscape. Joshua Tree is, in a sense, an older version of the Sierra Nevadas, with the characteristic Inselbergs representing the erosional remnants of much larger masses of granitic rock. Inselberg, remnant of part of a batholith. Roof pendant, country rock, capping intruded rock. Veins, cutting across granite. At Joshua Tree, 3 types of veins can be found. Pegmatite contain very coarse-grained feldspars and quartz. Quartz, which may also hold gold, silver, and other valuable ores, and aplite, made up of fine-grained feldspars. Metamorphic rocks make up a significant portion of the Joshua Tree landscape. Generally speaking, this rock makes up the mountains surrounding the basins containing the park's main attractions. Metamorphic rocks form from the alteration of pre-existing rock. Intense heat and pressure cause the minerals to align themselves, creating the distinctive foliated texture of metamorphic rocks. The Pinto gneiss represents some of the oldest rock in western North America and formed during an ancient mountain building event associated with the assembling of an ancient supercontinent, Rodinia, 1.7 billion years ago. Up to this point, the evolution of the Joshua Tree landscape has been described in terms of constructive geologic processes. These are driven by Earth's internal heat, which causes plate tectonics and the formation of magma, volcanism, and tectonic uplift, resulting in adding new rock and building up the crust. Working in opposition to constructive processes are destructive geologic processes. These external processes, like weathering and erosion, operate on Earth's surface to wear down and shape landforms. Weathering causes the breakdown of rock on or near Earth's surface through mechanical or chemical actions. Mechanical weathering involves physical processes that cause rock to crack into sets of fractures called joints. Rocks in Joshua Tree are commonly jointed. Chemical weathering causes chemical reactions which alter and dissolve minerals in rock. Hydrolysis is a chemical weathering agent that converts feldspars in granitic rock to clay, leading to a type of weathering called spheroidal weathering. Spheroidal weathering has played a crucial role in forming the Inselbergs and boulder piles throughout the park. Spheroidal weathering happens along joints. As magma cools and contracts, joints can develop. Later, as the intrusive igneous rock is brought closer to Earth's surface, the removal of overlying rock releases pressure, allowing the mass of granite to expand, causing another set of joints. Additional joints could develop from tectonic stresses acting on the body of rock. The result is rock fractured into cube-like pieces. When the rock is close to Earth's surface, acidic water will flow along the cracks, preferentially weathering the corners and edges. Imagine how an ice cube in your mouth becomes more rounded as it melts. The rounded cubes are exposed after the overlying weather rock and soil is removed by erosion. Spheroidal weathering has resulted in making the boulder pile hills and Inselbergs that characterize Joshua Tree's unique landscape. Tectonic uplift is a constructive geologic process that plays an important role in driving the evolution of the Joshua Tree landscape. The San Andreas Fault was established about 25 million years ago. Since that time, its configuration has changed, with the Big Bend starting to develop around 6 million years ago. This geometry plays a major role in the tectonic uplift of the landscape in Southern California. Along the bend, compressional stresses are squeezing up the crust as the Pacific Plate tries to slide past the North American Plate, resulting in uplift of our local mountains. Significant faults influencing the landscape of Joshua Tree include the Pinto Mountain Fault, which runs parallel to Highway 62 and is the cause of the Oasis of Mara. The Blue Cut Fault has created Pleasant Valley in the central part of the park and could have facilitated volcanic activity. And the San Andreas Fault, which is driving the uplift of the Transverse Ranges. Note the Oasis of Mara and the Visitor Center. The San Andreas Fault, as seen from Keys View. The landscape of Joshua Tree has also been influenced by climate change. It was cooler and wetter during the past 5 million years or so, which means there was more vegetation and a thicker soil horizon. Tectonic uplift of the local mountain ranges has put Joshua Tree in their rain shadow, causing warming and drying of the region. We are also entering an interglacial period, which means a warmer and drier climate, which is further exacerbated by human-caused global warming. What this means for the Joshua Tree landscape is less vegetation to protect the soil, resulting in greater erosion. This increased erosion has exposed the spheroidal weathered boulders and inselbergs, and has facilitated the development of pediments and alluvial fans. Pediments are relatively flat, eroded surfaces of bedrock. Alluvial fans form at the base of mountains in arid regions experiencing tectonic uplift. During flash flood events, sediment is transported from the mountains to a relatively flat valley where it slows and deposits its load of sediment. Soil notches and dissolution marks provide evidence for erosion of the thicker soil horizons that existed during the past wetter climates. This illustration summarizes the formation of soil notches and dissolution marks. This process is partly responsible for the famous Skull Rock. That's it. Thank you for your attention.